Okay, are you able to see now?
Not yet, sir.
Huh?
Not yet, sir.
No, sir, not yet.
No, sir.
Maybe I think I didn't share. Okay. Okay, so now you can see, no?
Yes,
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 sir.
yes, sir.
Okay, make it full screen.
Yes.
Okay. Okay, so this class we'll continue with one more algorithm for two variable optimization. So this is called Fletcher-Reeves conjugate gradient method, and it is an improvement over the Powell's method. So in the Powell's method, um, three searches are required, line searches are required, but in this Fletcher-Reeves method, only two line searches are required. But you need to have the first derivative calculation. Also, the formula for Fletcher is more complicated than Powell's method. So for Powell's method, you first do one line search like this. Okay, then you do another line search like this. Okay, and then okay, say M1, M2, another third line search like this. But in the Fletcher method, you do one line search like this, and then using a and you find M1, and then using a special formula, you can search along this line and find the minimum. So this extra line search is not required in the Fletcher-Reeves method. Okay, so here we need to use first derivatives. So the line search is first done according to the steepest descent vector. So the first search vector is nothing but the steepest descent vector from our starting point x0, y0. So in that it is similar to the Cauchy steepest descent method. Okay, so S0 is obtained like this. So what about the next search vector? S1, S2, etc. So the S1, S2, etc. are calculated using this Fletcher-Reeves special formula. Okay, so here K is the current iteration, K minus 1 is the previous iteration. Okay, so here you have S0, and here you have S1. So after you find S0, you have to find all these things. This is the absolute value of the del F vector at x0, when at x1. Then this is the absolute value of del F vector at x0, and this is the negative of the del F vector at x1. So all these things have to be substituted in this complicated equation, and then you get the next search vector. So this search vector has to be substituted in the objective function, and you have to do the next line search. Okay. Then just like Powell's method, these two search directions will be conjugate directions. So that ensures that you will quickly reach the minima instead of zigzagging at right angles. Okay. So successive values of x1, y1, x2 points are calculated by line search. And in case of quadratic function, just like the Powell's method, minima is quickly reached after these two line searches. The comparison between steepest descent and the conjugate direction method. So you can see that the conjugate direction method for Fletcher is the red color. So it will find the minima for quadratic function in just two steps. So this is one, this is two. Whereas the steepest descent vector in the green color will, uh, continue zigzagging like this, okay, for a long time. Okay, so now let us look at one solved problem. That is a simple quadratic function where you are supposed to get the minima in two line structures. Starting point is also given. Okay, it is 0, 0. Okay, so as per the method, first line search is from x0 along s0. S0 is the steepest descent vector. So this is S0. So this red line is the steepest descent vector S0. And after you do line search, you find x1. So from x0, you find the x1. How do you do this? So this is S0, initial steepest descent vector. So that is minus of del f at x0, y0. So minus of del f is okay, minus 1 and 0. So the parametric equation of the steepest descent vector is starting point plus h into del x and del y. Okay, so the so these have to be substituted in the objective function and minimize. Okay, so you get h star is equal to 1 by 8. And if you substitute the h star in this equation, you get the next point x1. X1 is minus 1 by 8, 0. Okay, that is this point. Okay, then what is the next search directory? S1. So this one is calculated from Fletcher-Ree formula. Okay. Fletcher-Ree formula. So that is what we are going to look. Okay, so you found x1. Okay, x1 has been found out, minus 1 by 8, 0. Okay, S1 has to be found out. So this is the formula for S1. And you have to substitute all these things. Okay, for example, S0, this is the previous search vector. Okay, this is occurring here, and this is the absolute value of del f at x1. This is the absolute value of del f at x0. This is minus of del f at x1. So you substitute everything here. You do simplifications, and this is the equation of S1. Okay, S1 equation or the direction of S1. Okay, that is minus 1 by 4i and minus 1 by 2j. So this has to be expressed in parametric form. Okay. Okay, so S1. Write S1 in the parametric form. That is the starting point plus h into this del x, del y values. Okay, so this is the del x, del y values. And you get the parametric form of the equation as x is equal to minus 1 by 8 minus h by 4, y is equal to minus h by 2. So you substitute that in the objective function and do minimization. So you get h star is equal to 1 by 4. Okay, so and if you do the back substitution, you get the exact value of the minimum. That is minus 3 by 16 minus 1 by 8. So this is the exact minima because this is a quadratic objective function and also it is convex. Okay. Okay, so now this is the end of the optimization algorithms for multiple variables. So in all these algorithms, I taught only with two variables, x, y, but you can easily extend it to x, y, z also. For example, you can write x1, y1, z1 plus minus h into minus 1 by 4, minus 1 by 2, minus 3 by 4, etc. So you can add, you can keep on adding any number of variables. Okay, so that is one thing. Then another highly important thing which I didn't say up to now is that all these algorithms for multiple variables, eventually result in a single variable function, like minimize f of h is equal to 3h squared minus 2h plus 3. Finally, you will get an equation like this. So this is the slice of the objective function above the line search vector. So this is solved by algorithms using what is that called? That golden section method. Okay. So although the problem may be a multivariable problem, in the end it is solved by a single variable algorithm like golden section method. Okay, we can stop this topic and go to next topic. Okay, so next we go to MATLAB optimization toolbox. So as per the syllabus of this particular course, this thing is included. That is why I am teaching this. Then for the assignments, you have to manually find the minima of an objective function using Cauchy's method or Fletcher-Reeves method and compare it with the results you get from the MATLAB optimization toolbox, and both must match. So that is why you need to study this thing. Okay, let me go to.
Sir, in exam, like, are we allowed to use the MATLAB, sir? Or
The
we
exam is only for hand calculation. Only assignment you have to use the
Okay, sir.
MATLAB. Okay. So introduction to MATLAB optimization toolbox. Okay. So the first few pages are just some basic introduction. So handling vectors and matrices in MATLAB. So this is important because you have to specify the vector of the constraints and the vector of the variables and things like that. So actually all MATLAB variables are designed to be vectors or matrices by default. So when we give them single values, they become scalar. Okay, for example, I write x is equal to 1 in MATLAB. But actually, this x is initialized as an array, like first value is 1 and all the others are set as null. Okay? So MATLAB deals all variables as vectors for matrices. So even if you write x is equal to 1, it only initialize the first value of an array to x equal to 1 and sets all the other to null value. So these values are all there in the background, although they are not used. So this is the meaning of saying all MATLAB variables are designed to be vectors or matrices by default. Okay. So let us see how you can type in a matrix, because you have to type in the matrix of equality constraint, inequality constraint also. So suppose I want to define a matrix of size 3 into 3. So one method of filling the matrix is to enter the elements one by one. Okay, that is A11 equal to 2, A12 equal to 3, A13 equal to 4. Then you type A21, A22, A33. So this is very tedious. Okay, so people don't use like this. So in the MATLAB, they are easily entered like this. So 2, 3, 4 is first row, 5, 6, 7 is second row. This is actually third row. And the semicolon will make a new row. Okay, if you put semicolon at the end of 2, 3, 4, it means that that row has ended and new row will come. Okay, then you can also write 2 full colon, 3 full colon, etc. Or you can use blank. Okay, so actually nobody uses this full colon. Instead, they use the blank to separate the numbers. Okay, so after you enter this definition of A, and then you just type A and press return. So then it will show the contents of A. So if you type any a variable name like X, Y, or A and press return, it will display the contents of the numbers stored in that variable. Okay, then we can also assemble sub matrices like this to make a full matrix. Like you say, the first row, this is the row matrix A, this is row matrix B, this is row matrix C, and A is the assembly of this row matrix. So this can also create this big A matrix. Okay, then how you generate row and column vectors? Okay, so for example, you write A into X is equal to B. So this is actually a column vector. Okay, so how do you define X and B? So to define a column vector like 12, 25, 6, 7. Okay, so after 12 you put a semicolon indicating that row is over. Then after 25 also you put semicolon indicating that row is over. So that is how you, and then after that if you type F and press return, it will show the contents of the vector F. And how to make a row vector? That 12, 25, 6, 7. Okay, then you can give the gaps between the rows. So that will give a row vector like this. So these are this row vector and column vector are important. Okay, and also after you define a matrix A, you can use this command. For example, dit A means determinant of A. Ig A means eigenvalues of A. And it will give eigenvectors also. So this is just an example. Okay, so then if you type inverse of A, INV of A, it will give inverse of A. A apostrophe will give transpose of A. So this is just a brief example of how you can use inverse of A. Now suppose I want to solve this equation, that is A into Q is equal to F. So A is known, F is known. Okay, so this X, Y, Z has to be solved. Okay, so A into Q is equal to F. So Q is equal to A inverse into F. Okay, so first you define this matrix A. Okay, so 1 minus 1, 1, 1 minus 1, 1. Then you put semicolon to indicate that row is. Put a semicolon to indicate this is row. Then 3, 2, 0. Okay, then how do you define this? A column vector F. So after 20 you put a semicolon, 42 you put semicolon, etc. So that means after 20 that row is over, after 42 that row is over, etc. Then you type this Q is equal to inverse of A into F. Okay, that is this thing. Inverse of A into F. And then if you type Q, or the values of X, Y, Z will be stored in the Q, and you can see it displayed. So this is shown just as an example on how to enter the rows and columns of a matrix for the optimization subroutines. Then initialization of matrices to 0 or initialization to identity matrix. So if you type zeros mn, it will make a 0 matrix of the order m into n. If you type in, it will produce a identity matrix of order n into n. So these are all examples of how to use the commands. Okay, so example of making an identity matrix of order 3. So you type A equal to I3, and okay, so then the identity matrix value is stored in A. And if you type A and press return, the values of A will be displayed. So you can see that this is a identity matrix. So any Any matrix when multiplied with an identity matrix will give. That is the specialty of the identity matrix. Okay, now we look at MATLAB optimization toolbox. So we are going to study all these things, okay? World programming. So this we are not going to look, okay? Okay, then I also forgot, okay, there is genetic algorithm routine. That also we look. Genetic algorithm subroutine in MATLAB. Okay, so first is that before you call any optimization subroutine, whether it is for linear programming problem or genetic algorithm, first you have to use this optimset function to set the default values for the subroutine. So what are the default values for the subroutine? Just the number of iterations to convergence, then the tolerance of the final answer, then display options. Display option means, do you want to see all the iterations or do you want to see only the final answer? These type of things are called display options. So that is the first thing. You have to call this optimset function. And then second is that you have to define the objective function. So fun of x, okay, is defined as the objective function. Okay, so in this particular case, our objective function is x squared plus 2x plus 1. So that has to be defined either by this function statement. So this is one option. You can type this one line and define the function statement. Or the objective function can be separately defined in a fun.m file, which returns the objective function and supplied with the design variable vector. So suppose your objective function is a very complicated function, like you want to find the efficiency of the IC engine. So it can't be written in one line. So there you open another file called fun.m and then you write the objective function in such a way that when you input with the design variables like pressure, temperature of the gas, etc., then it returns the efficiency of the engine. So that objective function subroutine can be written in a separate file called fun.m. And if it is a brief objective function, you can write it in a single line within the main code itself. Okay, so that is the second thing. That is the objective function definition. Then third is a you have to define the equality and inequality constraint coefficient matrices. Okay, for example, equality constraint matrices are written like this: A equality into X is equal to right side, B equality. Okay, then you can do the matrix of inequality constraints. For example, I write 2x plus y is equal to 1. X minus y is equal to 3. So this is the vector of equality constraint. So A matrix is 2, 1, 1 minus 1. And B matrix is 1, 3. So this has to be defined here, okay? And suppose it is inequality constraint matrices, like this. So then same can be written as the inequality constraint coefficient matrices. Okay, so this is the third important thing. All this information has to be given to the algorithm. Okay, so now I think for this class we'll look at this linprog, that is linear programming problem. So this problem is specified by minimize f of x. So this program will only do minimization. If you want to do maximization with this program, you have to take the negative of the objective function and do minimization. So it will do the maximization. So, okay, minimize f of x, where x is a vector of design variable like x, y, z, etc. Or it's a length, breadth, height, etc. Subject to the equality constraint matrix, subject to inequality constraint matrix, and then you have to define the upper and lower bounds of each design variables. Okay, that is x, y, z. Okay, x is between 1 and 2, y is between 0 and 10, z is between -1 and 10. So these are the lower bound. These are the upper bound. So all this data has to be supplied to the program. Okay, so this is the definition of the linprog subroutine. So before you use linprog, you have to use this thing. You have to type options equal to optimset linprog. So this will load all the default parameters of the linprog subroutine. Okay. So in the modern version of MATLAB, you can type like this also, but both will work. Okay. So we can also give individual customized options. Okay, for example, optimset display set as off. Display set as off means it will not give all the iteration information. It will only show the final answer. Then maximum iteration 100. So it will stop after 100 iteration. Then tolerance, that is 10 raised to minus 5. Tolerance means is the difference between the objective function results in each iterations. Okay, between successive iterations. Okay, then you can call linprog. So first you have to set the defaults. First set the defaults for this, then call linprog. Okay, so how does the linprog subroutine work? This is the linprog subroutine. The f is the vector of coefficients of the objective function. A and B are the coefficients of the inequality matrix. Okay, the A equality and B equality are the coefficients of the equality matrices. And LB, UB are the lower bound and upper bound of all the variables. X0 is the vector of starting values. Okay, so usually you saw in all our previous algorithms that user will give a starting value. So this is that starting values. Then okay, these are the default values. Okay, options. So first you have to type this, and this will be automatically loaded into the subroutine when you type options into the subroutine definition. So we'll solve one problem with this answer. Okay, minimize this objective function fx, that is -5x1, -4x2, -6x3. So F matrix is defined like this. Coefficients of the F matrix are -5, -4, -6. Okay, then we have only inequality constraints. Okay, in this problem there is no equality constraints, only inequality constraints. Okay, so this is actually the A matrix. So this is 1, 1, -1, 1, 1, -1, 1. This is 3, 2, 4, 3, 2, 4. This is 3, 2, 0, 3, 2, 0. And this is 20, 42, 30, 20, 42, 30. So the coefficient matrices for the inequality constraint has been defined. Okay, then there's no equality constraint here, and we give this null value for the coefficient matrix of equality constraints, and we give null value for the coefficient the right hand side coefficient matrix of the equality constraint. It is set to null. So this means no equality constraints. Then you have to define the variable bounds. So x1, x2, x3 are our 3 variables. We know the lower bounds, okay? Because this is some engineering problem. We know that lower bound is 0, 0, 0. It cannot be negative. But upper bound we don't know. So because upper bound we don't know, UB upper bound we don't know, we equate it to null matrix. Null matrix means two square symbols like this will give the null matrix. So UB we don't know, so we equate it to null matrix. LB we know. Okay, so LB is this column matrix 0, 0, 0, 0. LB is not, UB is not. Okay, then what are the starting values of X? Okay, X naught. So we don't know starting values. Okay. Usually people will give 0, 0, 0. But if you don't know, you can set it as null. Then the algorithm will use its own logic to find a suitable starting value. Maybe it will do some random search and find some suitable value. But if you don't know, you set it to null. So now the code will look like this. First you type options equal to optim set lin proc. So this will load the default options. Okay. Then we have define the F matrix, then A matrix, B matrix, then lower bound is 0, upper bound is set to null, we don't know. Starting values is set to null. Then equality constraint matrix is set to null. I mean the left hand side of equality matrix set to null, then right hand side is set to null. So this is how you call the subroutine. Okay, lin prog F A B A equivalent. So all these things must be defined. Okay, must be defined before you call the subroutine. And on the left hand side, the answer of the X values will be stored here. Okay, the variable values will be stored here. Okay, and F value is actually objective function value. That is the minimum value of the objective function is stored in F1. Okay, so after you type this command, you can press return, and then it will solve the things. And after that, you press X and type return. Press X and type return. So inside it, the values of X1, X2, X3, that is the optimum values of X1, X2, X2 will be stored. And then you type F1, that is the objective function value, and you get it as -78, which is the lowest possible value. Okay, so this is how you do the MATLAB toolbox for the linear programming. Okay, we can stop here now. So I'll take the attendance.